When your program needs to read a file, the normal path involves a lot of copying. The kernel reads from disk, copies data into a buffer, then copies it again into your program's memory. mmap skips that whole dance. It hands your process a chunk of virtual memory that points directly at the file. Welcome to Awesome Linux TV. Let's break down how that actually works. With a standard read syscall, your program says, here's my buffer, fill it up. The kernel pulls data off disk into its own internal page cache, then copies that data byte by byte into the buffer you provided. That's 2 full copies of every byte, one into the kernel space, one into yours. For a small config file, you barely notice. But for a 2 GB database file, those copies burn CPU time and memory bandwidth that add up fast. mmap tells the kernel, reserve a range of virtual addresses in my process and point them at this file. No data moves yet. When your program actually touches a byte at that address, the CPU's memory management unit looks up the page table, sees nothing's loaded, and triggers a page fault. The kernel steps in, loads just that 4 kilobyte page from disk into physical RAM, updates the page table, and lets your program continue. From your code's perspective, you're just reading a pointer. The OS handles everything behind the scenes. Here's the sequence the first time you touch an mmapped address. Your process dereferences a pointer. The hardware MMU checks the page table and finds no physical page mapped. That's a page fault, a trap into the kernel. The kernel figures out which file and offset the address corresponds to, loads the relevant 4 kilobyte page from disk into a free frame of physical RAM, and wires up the page table entry. Then it returns control to your program, which picks up right where it left off. The whole round trip takes microseconds on an SSD, and after that first access, that page lives in RAM and the kernel's page cache. This lazy loading is called demand paging. If you mmap a 10 GB file but only read the first 100 bytes, only the pages covering those bytes get loaded, maybe a single 4 KB page. The kernel uses the same page cache it maintains for all file I/O, so other processes reading the same file share those cached pages in RAM. When you write to a private mapping, the kernel copies just that page, a technique called copy on write, so you still don't pay for the whole file. And if RAM gets tight, the kernel can evict clean pages since it knows it can always reread them from disk. Here's the simplest working mmap example. We open the file and stat it to get the size. mmap needs to know how many bytes to map. Then mmap takes 6 arguments. Null for the address means let the kernel choose the size is our file size. Prot for it says we only need to read. Map private keeps our changes private, and the file descriptor and offset 0 rounded out. The return value is just a char pointer. We print the first 10 characters. That dereference is what triggers the page fault we talked about. When we're done, mmap releases the mapping and close releases the file descriptor. The whole thing is under 20 lines. mmap really earns its keep on random access workloads. Think databases jumping around a multi-gigabyte index file. It also shines when 2 processes map the same file and share those cached pages, which is how shared memory libraries work on Linux. But for a simple sequential scan of a massive file, read with a good buffer can actually be faster because the kernel can optimize the I/O pattern. And if you're doing lots of tiny reads, the per page fault overhead adds up. A buffered read amortizes that cost across bigger chunks. The right tool depends on how you touch the data. mmap blurs the line between files and memory. Your program sees a pointer, the kernel handles the disk, and the hardware page table does the wiring. Next time you're reaching for a read on a big file, consider whether mapping it might be simpler and faster. Thanks for watching Awesome Linux TV. See you in the next one.